Hello and welcome to the ASC video series. I'm Dr. Sean Perry. This is Introduction to Statistics, STA 2023. We're going to look at some problems from Chapter 6 concerning the normal distribution. So before we talk about what is the standard normal distribution, we should talk about first, what is a distribution? So a distribution is any positive curve, the area under which sums to be 1. So the normal distributions are a family of curves that have this kind of bell shape. Now, the one that I'm showing here is the standard normal distribution. It has a standard deviation of 1 and a mean of 0. And those numbers factor into this equation, that you really have just a lot of scaling parameters in here. There's a lot of constants. The real meat and potatoes of this is that you have e to some negative power, and that is a square of some variable. So you have e to the minus something squared. That's it, e to the minus something squared. And that will produce these kinds of curves. Now, notice also that the x-axis and the y-axis have different scalings in order to make it look like this. If I just turn on the regular 1-for-1 scaling, we get this kind of depressed curve, which we usually don't see in the textbooks. Now, we can allow these parameters to vary. The smaller my standard deviation, the spikier my bell curve. And the larger it gets, the flatter. No reason to have this centered at the origin. It could be allowed to move. And all of these curves are normal distributions. They're all bell curve. If you want to note one last interesting thing about the formula, notice that here we have the equation for a z-score. We'll talk about that more later. So really, this is just a change of variables from x to z. What do we do with these? Well, one of the things that we do is calculate the area between two values. Remember that for a probability distribution, the way you interpret this area is the probability of getting a value in this range is equal to this area. So there's always this relationship between probabilities and areas. The probability of getting something over a certain range and the area under the curve inside that range. Notice that if I set this to a point, I will get area 0. So the probability in any continuous distribution of getting a single output is always 0. Notice also if I set this to 1 and this to -1, we get an expanded version of the empirical rule, which says that between one standard deviation, we've set that equal to 1, away from the mean, we're going to have about 68% of our data, actually 68.27 approximately percent of our data. So let's look at some problems concerning the standard normal distribution and how we'd go about solving them. So it says, given a standard normal distribution, determine the following probability, round the solution to 4 decimal places. So we want to know the probability that z is going to be inside of this interval. So I always like to begin these problems with a sketch, right? You just don't need to be too artistic here. Just throw out a simple bell curve. And if it's a negative score, we could put it on the left-hand side because 0 is going to go right in the middle for the standard normal distribution. And negative score, well, I'll put that down here somewhere. And a positive score, well, that's a pretty big positive score, so I'm going to put that way up here. And the question they want to ask is really, what is this area? This probability and this area are the same. That's the power of a distribution. You calculate an area, you get a probability. So how could we go about doing this? Well, first we'll look at a table version, and then we'll look at a calculator version of doing this. So let's talk briefly about how to look up a certain probability in the chart. Let's say we knew that our z-score was between these two values. If we go to look these up in a chart, what we're going to find is the left-handed areas. So let me just give an example of some Z1. The chart will tell us this area here. And if what I really want is the area between the two of them, let's say Z1 here and Z2 here, how can I get that from the left-handed areas of each? Let's say this is Z2 here. So what we'll do is take away this area here from our Z2, and what I will have then is just the area between them, right? This area here. So what do? We take these two values, look them up in a chart, and then we take the difference. So let's compare that to our problem here. If I look up these two values in my chart, here is a chart. So how are these values arranged? Well, they have the first couple digits, the ones in the tenths place here, and then they have the hundredths place along the columns. So to look up a number like minus 0.28, what we need to do is find, well, let's find the hundredths place first. That's 8. So we're going to be looking in this column. And now we're going to find the first two, which is minus 0.2. There we have it. So we have 0.3897. In other words, this area here is 0.3897. We could look up the area for Z2, 5.92. So we have a 2 in the hundredths place. That's going to be this column. And then we go down to 5.9. Uh-oh, it's right off the edge of the map. That's pretty close to 1, so you can just assume if it's off the edge that it's 1. But this is just one more reason why I generally don't like doing the table methods. They are only so big. And so if I get something right off the edge, like 5.92, it doesn't tell me exactly what it is. I'm only left to infer that this area is pretty much all of it, which means it is 1. We take a difference and get 0.6103. There we go. All right, so let's look at a different way of doing this. Let's look at how we would address this on the calculator. We're talking about a distribution, so we're going to go to second vars, which gets us to distir, and we have normal PDF and normal CDF. We're going to go to normal CDF, and it wants us to give lower and upper bounds. It also wants to know the mean and standard deviation. When we're talking about the standard normal distribution, these can stay as 0 and 1. This is if you're using z-scores, for example. So we have a lower. Our lower z-score is going to be minus 0.28. Our upper z-score is 5.92. And we go to paste to put this on the command line. What this has done is it's actually filled out a command, normal CDF. So if you're on a TI-83, you'll just get this command and have to put these in this order. But you put your first z value or x value, then your second, and then, you know, the mean and standard deviation. If you don't put 0 or 1 here, it will just assume that those values are 0 and 1. So you can, if you're just using the normal distribution, just put a parenthesis right there for the standard normal distribution. And then we also get it out to a greater number of decimal places, which is nice. But you can see that this, when rounded, is just our tabular value. Okay, let's look at another distribution. It's normal, but it's not the standard one. We've been given a different mean than 0 and a different standard deviation than 1. But after scaling, this is just going to look like a normal distribution curve. And we are interested in the area between two values, 79, which is less than 86, so I'll put that over here, and 93, which is bigger. I'll put this over here. And now notice that I've drawn one dotted and one solid to respect the strict inequality or the less than or equal to inequality. But the area of those lines, what they contribute to the area between the curve is nothing. Area of that slim line is just 0. So there's no difference when you have different combinations of equality or lack of equality down here. You will calculate everything the exact same way. But this is our question, is what is this area? There is a correspondence between these two things. Now, in order to use the chart, what you would do is first convert these values into z-scores. So let's look at the formula for a z-score. I'll call this Z1 to correspond with my X1 here. And this is going to be X1 minus the mean divided by the standard deviation. This is our formula for Z. You can find that here in your formula sheet, in addition to the formula that basically just solves this for X. And essentially what we're doing is changing variables. We're going from talking about this in terms of X to talking about this in terms of Z. But we're going to calculate the area the same way. It's just we already have a table for the standard normal distribution. So we could type that into a calculator and get minus 1.4. We do the same thing for Z2. We get positive 1.4. Then we're going to look up these values from our table. Minus 1.4 is minus 1.40. So we start in this column and go to minus 1.4. There it is. So 0.0808. And positive 1.4, 0.9192. We take a difference to get our answer. Notice that the value is slightly different in this accepted answer, and that's okay. There is a bit of tolerance that's built in to each one of these to deal with the rounding error that occasionally comes up when you're using the table. It doesn't mean that you've done something wrong. It means that this answer was also close enough to get counted as correct. Let's see if we can get their answer that was input here by using the calculator. So we're going to head back to second, distributions, normal CDF, and now we're going to put these things in. 79 for our lower, 93 for our upper, and now we're just going to change the mean and the standard deviation. Now you could also use the z-scores that we calculated here and put those in for your lower and upper and just keep this standard deviation. Also fine. Also would give you the same answer. But if we're going to put these in, we're going to need to put the mean equal to 86 and the standard deviation equal to 5. And here you can see that if you're able to take this to 5 decimal places, which the table also cannot do, and then round it appropriately, you would get 8.5 instead of 8.4. This is what I mean by a rounding error when we start to use the table values. These two values over here were already rounded. And then taking their difference, we get something that has a bit more error than if you only round once.